That's cool. Why is that cool? Well, we can now compute the edit distance with the quadratic effort n times m, the two lengths of the corresponding sequences, instead of an exponential effort, which would be 3 to the power of something. And that is obviously a really, really huge boost. So this programming dynamic scheme is very helpful in that case. And once again, we can just start at the top left, and then fill in the first row, first column, then fill in the first row, second row, second column, third row, third column, and so on and so on and so on. And at the very end, according to this closed formula here, and at the very end, we have the edit distance in the lower right corner. Very good. Also a nice thing with the edit distance is, or with this procedure, is that from this matrix of these sub-alignments that we fill in during the computation, we get the optimal alignment also. So one of the side constraints, or the collateral damages, of course, of the edit distance is that we have to compute the optimal alignment between the two sequences in order to get the edit distance, because the edit distance is the cost of the edit operations for the optimal alignment. So and we can get that actually out of this matrix, and that is another nice so to say free collateral damage, a positive damage in that case, obviously. And we'll see how that actually works. So it is very easy, because a cost minimal path through D from 0, 0 to NM, so from left upper corner to right lower corner, right corner, such a path yields the optimal alignment of these two sequences. So in that case, for example, we can go from here to here to here to here to here, which represents the optimal alignment between the two sequences Tor and T, and basically we get the alignment of T and T, and then actually we have two options, basically going this or going this and this and this. So basically we have to align R to R, and we can do with these two intermediate steps here, I, E, and O, we can do different things actually. So there may be a non-determinism in the whole thing, because we may have several cost minimal paths representing different optimal alignments, obviously, and that is basically quite easy, I think. I mean, we can introduce this artificial placeholder in between here or here, because here we have two things in between T and R, and here we have only one element or one element in between T and R. So we have to introduce one of these artificial, or an artificial element here in between, in order to somehow account for those two here. And we can do that here or here, and that's obviously both optimal in that case. So the number of edit operations remain the same. We can map, or we can replace O by I and the placeholder, so insert E, or we can insert I and replace O by E. So that is the same, and that is this non-determinism in that example here. So there may be several of those cost minimal paths representing all the different optimal alignments actually. And the optimal alignment can be obtained by backward reconstruction of the decisions that we made at each step along the optimal path actually. So the decisions that we did can be stored during the matrix construction from top left to lower right corner. So we don't have to go through the matrix again to do it a little bit more efficient, but that's just a kind of side information for you if you want. So here's another example with the Türschloss and Abschluss that we had before, and you see again here. So we start with the empty sequences, so to say. So we have in the upper left corner we have the 0, and then for example, if we go we fill in the first row and the first columns, the first column as we said before. If we go in this direction, we would insert T, Y, R, and stuff like that. Sorry, delete T from this sequence. So this row actually represents the added costs when we transform the corresponding subsequence of Türschloss up to the whole sequence Türschloss into an empty sequence. So if we only have T, we have to delete T. If we have T and Ü, we have to delete T and Ü, so we have two operations. If we have Tür, we need to delete 3, and so on and so on. So at the end, if we have the entire Türschloss sequence, we need to delete 10 elements in order to match or to transform Türschloss into the empty sequence. So that is represented by the first row here. The first column is the other way around. If we want to transform an empty sequence into R, we need one insertion of R, or into RB we need to do 2 insertions, A and B. So we have 2 operations, up S3 and so on and so on. So if we want to transfer an empty sequence into Abschuss, we need to insert A, B, S, C, H, U, S, S. So we need 8 insertions, in that case 8 edit operations. So that is the trivial thing, and then we can construct the next elements of the next column and the next row actually. So for example, this one here would be okay, as can be computed from this one here. So and that is actually a substitution, T by A. T is substituted by A in order to transform Türschloss into Abschuss. So in that case, this would add 1 to the diagonal element here. So that is the this case here. So that is a diagonal step, so to say. From here to here, from here to here, from here we're starting from here to here, it would be obviously deletion of T. That is this one here. So we add 1. So that is a deletion of T, adding 1, and from here to here, it would also be a deletion. An insertion of A. But anyway, okay. And we can fill up all that stuff here, and then we do that iteratively until we get that we filled the entire matrix here. And here, down here, we have the edit distance, the minimum number of edit operations that we need to transform Türschloss into Abschuss, which is 5 in that case. And here highlighted is just one minimal path, which corresponds to this alignment actually. So this is the substitution of T by A, the deletion of Ü, the substitution of R to B. So you see here, substitution, deletion, then again substitution. Then we have matches here when the costs remain the same over the diagonal. We have matches here. Then again, so a horizontal thing is always a deletion. So this is a deletion again, then a substitution again, and then again a matching here. So horizontal deletion, vertical insertion, and the diagonal steps are either substitutions or matchings, depending on the corresponding elements, of course. And you see we get this cost minimal path, which is so to say free from this matrix representation. Then there is a kind of variant which I just want to show you. It's not a big deal, but you can also weight edit operations through a so-called ground distance. So you can define different costs for insertions, deletions, and substitutions. This is especially interesting in the bioinformatics domain. For example, multiple insertions or multiple deletions could be penalized or whatever. And you need a ground distance here in that case. So the ground distance is delta here, and you can just incorporate that. So you see here, so this would be starting here. So the delta, this would be a substitution or a match. Yeah, so if it's a match, then it's here, so we don't have this delta here. So if it's a substitution, you could penalize that with some specific ground thing. Then the insertion could be penalized, and this is a deletion that can also be penalized. Yeah, and the same here. So all the deletions, if we go horizontal, can be penalized accordingly, and also the insertions, of course, again. Yeah, so you know from the corresponding arguments here that if it's a deletion or an insertion or a substitution, obviously. Yeah? So if the artificial element is here, it's a deletion. If the artificial element is here, it's an insertion, obviously. And if there is no artificial element, then like here, then it's a substitution. Yeah, so that is the easy way to decide how to define the ground distance. Yeah, so according to the arguments, you can define a ground distance, giving different costs for these three edit operations. Yeah, to round that up, so the properties of the edit distance is, as just mentioned, the optimal alignment of two sequences need not to be unique. So you see here, banana and band can be aligned in a cost optimal way in different alternatives. So here we have the three matchings and the three edit operations, like replacement, substitution, and two deletions, and the same here, which is a different alignment, but we also only have three operations, edit operations here, three matches and three, so in that case two deletions and one substitution. Yeah. So, but we talked about that before. Yeah, just don't get confused. The edit distance is very often also called Levenshtein distance. So actually this is not a typo. I think Levenshtein is really spelled like that. So Mr. Levenshtein is probably the one that defined the edit distance. So he actually came up with this formula here. But as far as I remember, he didn't actually propose a way to compute that efficiently, an algorithm to compute that efficiently. Well, this is a recursive formula, so you can, of course, implement that as a recursive program. But the real deal was, of course, this dynamic programming scheme where these recursive calls are materialized actually. Yeah? But anyway, so don't get confused. Levenshtein distance is also the same as the edit distance. The edit distance is a metric, which is, as we already mentioned, sometimes nice, sometimes just forget about it. But anyway, so the weighted distance, the weighted edit distance is also a metric if the ground distance is a metric. You can prove that. We don't do that, but anyway. Computation time complexity of a single edit distance computation is O of n times m for sequences of length n and m. With dynamic programming, space complexity is the same, but that's good. Yeah, and we had this common variant, especially in bioinformatics, that the first deletion of a symbol is more expensive than a repeated deletion. So you can also model that with a ground distance. In that case, the ground distance is not a metric anymore, and then the corresponding edit distance variant is also not a metric anymore. But very often you don't give a damn whatever on the metric property. But anyway, yeah, just that you know. So that's all for the edit distance.